Okay, first of all, hello and welcome everyone to now the third lecture of the Guerrilla-Lecture series. And today the topic search. So, first question for the intro. What does search mean to you? So, pick your favorite problem in computer science. Any other problem? Evan, what's your favorite problem?
So, DFS.
What?
DFS, and Queen's problem.
Ah, alright. And my favorite problem is natural language, for example. And now think about how this problem could not be solved with search. The cool thing is that search is such an ubiquitous problem in computer science that we can essentially solve most of the problems that we have using search. And the reason for that is the following. So here I just have some problem code. This is, for example, like a chess problem or something. When you usually write code, you tell your computer at every step exactly what it's doing. I mean, this is a bad chess computer, but essentially at every step or at every state of the board, it knows exactly what to do. However, in real-world tasks, this looks a bit more like this one. So we are adding holes into the code, and we kind of want the computer to figure out what the right next move would be. And because this is arbitrary part of the code that we can remove, that should be placed in there, this is what makes this problem so ubiquitous. So for computer science, essentially all our problems require search to be solved. In the last few lectures, we were developing a language that did essentially that one. So we had a language that had holes in it. Yeah, we called them variables, and we want to find assignments for these variables in order for the language to run. Now, all these nice features that we had required quick search, and I brought Guerrilla for the beginning. So my X is quick, okay. I is quick, just also T, and my machine is Y, mu wrong. Can someone, if the uppercase things are the variables, can someone see the solution of this one? Or did we have an algorithm with which we can solve these kinds of riddles? Yeah. This is a typical case of something that can be solved with our term matching algorithm, essentially. Yeah? So we just we build the abstract syntax tree for these graphs, or just take these sentences, lay them over each other, and the knowledge that some sentences have and others don't, we fill them up until we get to something that combines all the knowledge of the sentences that we had. Okay, seeing a few phases. So here the K would be to just also T, right? And then just would be put into the N, also into the U, and wrong would be into T, and so on and so forth. And then we get the whole finishing sentence. Essentially this is one integral part of search. So when we have something like this, where we can just see the solution from somewhere else because things just line up, then it's easy what to put. And that's the core feature of how we get good search. As long as we know what to put into our variables, we stay kind of clean and fast. So this is a normal constraint, right? So just a sentence with some part in it. When we would write this is X, then we just look into our knowledge base and know immediately what to put into the X. When we have several values, this can be kind of seen like a table. So when we just have one constraint on one variable and want to know what's into the what's going into the X, we just look it up in the above values. The whole thing also works with more complex values. So for example, when we have a list, like an element attached to a rest list, or some submit and else construct or something, we can also just look it up in this table, and then still there's some variables that stay open, but essentially we just see which constructor or which partial sentence has to be put in there. And I should mention that for questions, don't wait for me looking at you, just throw them in, right? Okay. Things though become complicated when several of these tables have to communicate. So say we have a table for what shall we do with the drunken sailor. When we ask several times the same thing on the same constraint, it's easy because then it always stays the same table. Meaning that if we find a value for the one, it's the same table for all. So it becomes complicated when several tables now try to find a value for the same variable. Let's get a knowledge base for this one. What we're doing in the morning. Here we wake up. They grab a bullet now, but it doesn't fit. So yeah, we grab a cutlet, and now we have in our program like a clause that is essentially combining these two tables. Right? So we have a morning table, Sharpie table, and in our memory you can imagine this. Yeah? So our memory is just like these blobbles of values, and in this clause we essentially have two pointers that point on the same thing in the memory, right? Meaning that if we assign it on the one hand, we also assign it on the other hand. If we start on the left with this one, we just look up this wake up value, put it in here, and the value is in here, and then if for example at some point we try to put the wrong value into it, then we can immediately see it because there's already a value in there, and this one gives a conflict. And in this conflict, we then just know that we have to switch the assignments on these tables, and we can do so by just picking the right value. Another way of how to look at this is also that we say, okay, when we push the wake up value into here, this value can now also be pushed onto all other constraints that subscribe to this one, right? So like the Shelby assigns a value, and then the morning also uses the same value. So I personally imagine it as if this value were now pushed into the morning thing, right? And now we only have to check whether the wake up is in the morning, and then we immediately go to the right value. We didn't even have to check the wrong one first. Yeah, and then we're getting some solution that fits for all. Okay, let's look at like a real world example to see like the tiny things that we can do in search and what happens when our programs and our languages are actually doing some search. The example I'm having here, so we have the sum predicate and length predicate. The sum essentially just it takes a list, and in its last argument it then says it adds up the elements, the contents of the elements, and we have a length that computes the length. The important part is that should pay up for. So we have I call them axioms or facts. So some cases that just holds without any condition, and some cases where if we say this constraint holds, also new constraints now hold on these new variables that we created. Okay. First a question to these functions because we're working with them for quite a bit now. Okay. So essentially sum. We say we take the sum of the rest list and add the first element, and length does pretty much the same thing, only that it only adds one for each element. When you actually build your compilers, it kind of looks like this one. So like you then have a pointer onto the same element in your memory, and maybe a pointer to the constants that we're putting here. The problem is that these are a lot of arrows, and it looks a bit ugly. So I came up with another visualization, and that is the following. So we have our memory blobs with the contents, and now we can put constraints onto parts of our memory. I indicate them with these lines. Over here you have a bit of overview of what's happening. So these are our two goals. We know that we have to find an L that is of length 2, and the same list should also have like the sum of its elements should be 3. Okay. When we now look into the constraints that we have here, let's start with the length one. The axiom doesn't fit because the last element needs to be 0. So there's only one case that could even fit into this L. So we're doing this, and we're unfolding the list constructor on this one. Now we know we've created two more variables, and so the first thing that we have to do is this length. Now, if it matches, then we also have to put these other constraints. I skipped the add constraint because it's easy, but like, yeah, so the length constraint is still put on here. So the rest list, the length of the rest list has to be, you know, one value lower than the length of the overall list. So this constraint is put here. We now do the same for the sum, right? Because the list constructor has now also been put to the sum constraint, and then the sum has its own constraint on the xs, yeah? Just with a value that we don't know. And the sum says, okay, the new sum is the sum of the rest list, which is this z prime, plus the sum of the overall list, which we already know. This is the 3. So we were searching for a list that has length 3. And now this ending constraint needs to add this x with the z prime and has to result in 3. So this is how we're putting the constraint onto the memory. Okay. Yeah. Problem is, what do we do now? There are several possibilities on things that we can put, and just for now, let's see. Okay, the sum constraint here, we have sum xs and z prime, so two variables that we can just arbitrarily assign, and this could fit well with our axiom up here, so that the sum of the empty list is 0. So yeah, let's try putting that in there. So now this value is assigned to the empty list, this value is assigned to 0, but now we're getting a conflict in another clause. So we put the length constraint in here, but the length is only the empty list if the result is actually 0, but we have said the result has to be 1, so there's a conflict arising. There's also only one way how to resolve this conflict now, because there are only two possibilities that we can walk in, so we do that again. Yeah, we split up the list again, we put the constraint here again, and same for the sum, right? So the sum constraint is also being put here, here you see a bit how these adds they interact. So first we add the x to the sum of the rest list, and the sum of this computation is then being added to the other x. And now finally we can actually use the length of empty list as 0 constraint, because we have a 0 here, and ta-da, we have the first end. Our search essentially stops when we have axioms on the ends of these ones, and every time we are putting such a constraint, all of these have to eventually only lead to axioms, right? So when we add an axiom, it's nice because we can stop at this part of the search. So this is an axiom. We now know that there has to be an empty list in here for this one. So we can also put the sum here. The sum takes the empty list, but now where we have the empty list, only the 0 can be put into the z double prime. So here is the 0. Can someone see the next axiom that we can put? This is a bit tricky to find. It's neither in sum nor length. It's in the end. The z prime becomes what? So if we add x prime to 0, in what would that result? So if I take a number and add 0, which number do I get?
Just get a sum. Just get a sum, doesn't it?
Yeah, exactly. So like this x prime and this z prime become the same value. So we're doing that, and this is an axiom of when we add 0 to something, the two values here become the same. Okay, but now we're running into a problem, because there's no more obvious things that we can do, because we kind of have to choose which of these x's we are now assigning to some value. As we're arbitrary, like both of them have some list for which is still holds. Let's just choose that this x prime is being set to 0. Why? Because then we have the case again that we have the axiom here. So like we have the 0 in the middle, meaning that the other two values are being put into the same place. The important part is that when two values are being merged to being one value, Also the term matching applies again. So like we take the biggest term in between them. So this is an arbitrary x, but here's a 3. And if we then assign the axiom, yeah, the value merges into the 3. And yeah, if we then check, you know, the length and the sum in between, it always comes to actions in the end. This comes to actions in the end. So like there's nothing more that we need to check. And we have found a solution. Yay! As these two terms are those that we observed, they are still the ones that contain the solution. So when you build your compilers, you don't like and actually do it with a scheme where you're just having pointers into your memory. You do not need to move the location of your initial query. Like the values are automatically propagated into it. And also, I kind of want to stress. I personally find this looks quite beautiful. I think we should do that a little more often in computer science. So yeah, when you're telling people that you're doing computer science, show them this one, and yeah, hide this one. So the same proof that we just did. This is the whole proof log. You can still read it. It's still like these sentences, but like yeah, it's getting a lot of clauses. But yeah, that's what actually happened. Okay, the general algorithm, so that we get a feeling for this one. So this is a DPL style algorithm. It's named by the creators Davis, Putnam, Lovelace. I always mix it up with 2 L's, but yeah, DPL style with a class name in it doesn't matter. It's pretty obvious if you see it. So the first thing that our algorithm does is fill all variables that can be uniquely filled. This is, we just look up in our tables, and if there is some table that says like this value has to be in there, right? We just put it. For this one, conflicts can arise. So you know, two different things say that there's conflicting values in our same variable, and yeah, we have to deal with these conflicts. And let us see that we would do this using something called class learning. Yeah. Eventually, when all these things have propagated and there are no conflicts left anymore, it can still happen that there's like still open variables. The first thing that we do is yeah, if all the propagation is done, put new constraints. So like when you have these rules, you first only deal with the left hand side of the rule, and when then everything fits, you put the right hand sides additionally as new constraints. These constraints can again, make other values unique again, and then we propagate this and so on and so forth. So essentially, this whole upper part here is all deterministic. So like essentially just like deducing the new values that are kind of obvious to our algorithm. All of this stays deterministic, and only in this last case, only when we have put all the constraints we can, when we have put all the values that are obvious to deduce, when there's no conflicts left anymore. There can still be variables that we just have no idea what to put. We saw that in the sum. It kind of depending on how we find these values first. There's always a solution, but we kind of have to choose where to start. And that's the general theme. So more visually, again we have tables with the same variable, and what we do in the unit propagation, this value has only one value. It's being put in here, and as soon as we change this value, it's also checked with all other constraints that subscribe to this value, and in this case, it fits. Now, this thing is a bit odd, because this doesn't come from unit propagation, but it could have been that at some point we just chose that this is the value that we want to try now. As soon as we put this value in here, let's say this table is maybe a bit bigger and couldn't have unit probation. But essentially, if we choose to put this in here, as soon as we check in this table, it would be a conflict, right? Because this is not the right value to put here. One way to deal with conflicts is to say, okay, in this conflict, we already saw which value should have been in there, and we just push it backwards. So we walk these arrows backwards and say, okay, like we now push the food in there, and then correct the error with this one. So this is why, for this case, it's kind of similar to unit propagation. We see in a second how it's getting a bit more complicated. The problem is when you always directly push the constraints back, kind of make the values bounce a bit. You can run in something like this. So here we enforce the breakfast is being put in here, there's a constraint here. This constraint says, well, your other guys changed, and it's being propagated back, and then this guy says, well, we've changed, and then we kind of, bobble in between those. This would mean that our structures wouldn't terminate. So we have to find a mechanism that makes sure that, that, for example, we're not running into combinations twice. And this one is one I'm making later. So, yeah. And in order to do that, we have to take a step back on how search actually works. When you're building your compilers for your search algorithm, this is essentially what you build. It's a predicate that takes the program and returns to you whether there's a result for the program and some proof of why it is the case that there's a result. More concretely, so for example, if the program actually carries a result, the proof is usually just a variable assignment that you can just read from a memory in that case. For the fourth case, that's a bit more complicated. I'm probably not going to that one today, but technically, if your search algorithm says there is no result, there is also ways of getting some feedback of why that is the case. But I'm interested currently in this last part because already knowing that there has to be such a search predicate gives us a negation. These search predicates can just be used as facts as any other. So we can say, well, as we want a certain program, a certain maybe incomplete program, to fail. That could be, so for example, if you're searching for errors in your code, you obviously want that the error search fails, right? Because you want no errors in the code. If that's not the case, you're getting hopefully the errors. Yeah, so essentially, not problem is just the fact of saying this program actually fails. And this is quite, it's weird on its own, but it can, for example, enforce a certain values on the case. Here we have an example. So the null predicate for the empty list obviously should return true. And for all other lists, we say, well, the list is not empty except if it is actually the empty list, because then it's a different case. So in some logical languages, these things are not read from top to bottom, so they kind of both hold at the same time. So this is why you here have to specifically say, it's not the empty list. We can even express a few more things with this one, just where we added already. We can make an if then else. Either the x holds and then the y also holds, but if the x does not hold, specifically the z holds, disjunction, so a or b or c or something. When you have disjunction of many values, you just say, well, at least one of them shouldn't fail, right? So you say it's not the case that all of them fail, essentially. And analogous to this one, how you write this depends on how you build your language, but so when you say that something holds for all values, it's not the case that it doesn't work, right? And failing succeed, they're just there can be handy tokens for your language to say, okay, now I specifically want to tell you to fail, or I want to specifically tell you to succeed. Okay, let's see how we can use this to prevent this kind of back and forth conflict pushing. And so we have here the same conflict situation, two tables, they cannot find an assignment, but every time we find a conflict, we just add it into our knowledge base that obviously this value cannot be a trace value. Then we propagate back. This one still works because there's a value off here. We say it can't be birds. Now we know it can't be flowers because there's something. Now this error would try to propagate back now, but there's no more values left that we can put into this middle variable, right? Because the trains and the flowers from this table, we've already shown them not to fit. It's important for your implementation that you implement something how even your clauses can communicate a bit, because you can see when you actually build this, it's kind of easy to treat each of these constraints kind of separately. But only when you look a bit onto the surrounding constraints, you can then actually say, okay, this value really does not have an assignment. And in your memory, it kind of looks like this, kind of beautiful. So you have one value, there's a lot of constraints on it, But you can follow these not constraints and then essentially read just check one table whether all of the table values have already been ruled out. So when you're for example choosing, you're never choosing values for which you already know that they shouldn't be in there. Right? That will be slow. Funny thing is, there is this weird case for sometimes you know that a certain value has to be in there, and then you have to kind of choose it. So if you're getting an equality without a not from somewhere, then you know that this equality now is being put in here. This is similar to the unit propagation, but yeah, just a fun fact on this one. And yeah, this is also how we can like really make a proof of non-existence by just saying, okay, there's one value where all the possibilities they never work. Okay, now back to this case. So sometimes in the unit propagation, it's just that like two values kind of at the same time push into the same variable. And what we can then do is like, okay, we say we don't assign this one first, but we do not know which of those values should change first. I know that these are currently just like single tables, but it could be that the value here is also a value that has been deduced somewhere else. So it could be that somewhere else in the code we could have actually changed this value if it, for example, was an assumption. So what we're doing is just we stop assigning stuff and we're adding the new clauses of saying either the left side has to change or the right side has to change, and then we go through the algorithm again. If we see okay this evening cannot be changed, then it's the things that created this evening value have to change, and so on and so forth, and we bubble that up until we find finally some half cut in this graph that actually changes. So if you have two things, they both have to change because these two things have to agree on a value for x. Yeah, this is this called clause setting, or something similar to this. So essentially you just add clauses where you say do literally anything that makes this conflict go away, right? And you just add this as a general constraint, then you keep on searching until you eventually find it. But yeah, so like this is a very nice approach because we're a bit careful. It's kind of like two people standing at a door and both of them saying, "Please go after me, no, after me," until you finally figure out what's going on. But sometimes I'm telling you. So there's another technique that I personally kind of like, and that is if we here introduce kind of like an additional variable that just immediately says which of these values has to change now. Because then we're giving priority to one of those, pushing one value here, and then through like the other propagation of our errors, this is now then propagated through here, and we can, through a very similar mechanism as unit propagation, push the error. Obviously, when then up here it says no, this value really cannot change, this makes a conflict again. This conflict propagates down here, and then obviously you have to change this variable, and then gets caught and it's being propagated in the other direction. This one behaves a little nicer in a concurrent setting because then you don't you don't have to check for so many clauses, and you're quicker in trying out stuff. But essentially it's still working similar to the unit to the clause line. Okay, but yeah, when we have propagated everything and did all that we could deduce, you will still find there is just things that you have to choose in the end. Like sometimes it's just that the solution doesn't matter which one you pick. Sometimes it's just like hard. There are actually instances that only have one solution, but it's not you can't deduce it with this unit propagation. And yeah, so then you have to choose. I'm not going into too much detail on how to do that, but one thing that is important for the choosing is it needs to stay complete. What do I mean by this? Following thing. This is, I think, one of the most done errors for students who are learning Prolog. Yeah, Prolog essentially always chooses this the first clause first, right, and then only the second one. The problem is that this first clause, if you always choose this one to be unfolded, you're getting an infinite list. and then you never get to any action, right? So you kind of have to be fair on which things to test. You sometimes even have to things that you just assumed, like change the value to see if there maybe you're getting to something. So this is why it's important to choose in a way that still that you still test out all possibilities eventually, or all possibilities that you cannot disprove, like that you cannot disprove that they cannot happen. But like everything that can happen, you eventually want to go there. Can someone think of an easy, like an incredibly easy solution to get this kind of completeness for your search? So probably it's one of my favorite ways to implement choose at random. Random is by the definition of random is like a random sequence is something that you cannot elaborate, and if you would know that the sequence would have something that would never happen, you could elaborate parts of the sequence. So like if you have something that's really random, you stay complete. Problem is when you're using pseudo-random generators, obviously they're not complete, but like this is something if you want to try some search properties. This one doesn't even perform that bad when you have all this unipropagation stuff, because you're only choosing things of which you couldn't deduce what to do anyway. Another thing, iterative deepening, just so you have heard the term. Essentially, we try out all combinations of old variables first. In that way, we only ever stick with like a finite search space of our old variables, and only when we checked all combinations for these ones, we head out to the other ones. This is not necessarily the fastest one, but at least it stays complete. There's another list of things that can be done. There's also a lot of research on getting incomplete search techniques that are just quicker, but just to give you an overview of what you technically need when you build these systems. Okay. We now had like kind of a funny system. It's not really like it is kind of a brute force search, but like it's also kind of smart when we like just constantly pushing the values back and forth. And just a pro to doing it like this. First of all, it can be parallelized. So if you have if you have a big instance and at two different positions, things just exchange values, and they don't interact. It's fine. Or like if they interact, you can even use threads or something to push the values from A to B, and you get something that's still working. Values only change if they need to, because we constantly have the graph of which value changes upon which value. We also only ever change the things that we really need. This is often like a weakness when you're doing systematic search, of just going through values, that sometimes you're just removing way more than you would need to remove. So this is nice. The only problem is it's kind of hard to stay incomplete, to stay complete, because you always have to have in your memory which assignments you already went through in order to make sure that eventually you go through all assignments. Okay, so let's have some review. What have you seen? So search on one variable is easy. You just look into your program and search, you look up the table for values that can be put in there, and then you put them in there. It becomes complicated with several values because they can then cause conflicts. We had a nice way of looking at it. So essentially all these the same variables can be treated as just the same positions in memory over which our constraints communicate. We had some algorithm that says, okay, first of all we have the unipropagation, so if there's only one value to put in here, we actually put it there. When we have conflicts, we add clauses that prevent this conflict from happening again, and doing the unipropagation again. If we choose in the right way, we eventually find a solution where all constraints are happy with what they with what they wanted to achieve. And one tiny thought I still want to give you on the way home. Everything is walking in parallel, and we have kind of a mechanism with which we can push arbitrary values to fairly arbitrary positions. What's with our knowledge base? The program that we write? Can we technically also change our knowledge base during the search? Any thinking? The knowledge base is just a term. So it can also be just an incomplete term with like still variables in it. And we can, as soon as we can access these variables, we can push values in there. And the question in science is not the why, but the why not. So when you have our solved predicate, it just takes the knowledge base as an argument, but the knowledge base can be incomplete, and then we can push things into this one. And next week we will be exploring a bit what we can actually do with this and how we can maybe optimize the solved predicate with it. That's it for me. Please search for questions, and thank you all for being here.